In the last few videos, we've been talking about the relation between the first derivative of a function and its graph so that we could predict behaviors of the graph by looking at different aspects of the first derivative. Now we're going to start mixing the second derivative into the mix. So let's take a look at what the notes have to say at the bottom of page 325 and into page 326. So it says here that the first derivative of a function identifies intervals where a function is increasing, decreasing, has a relative maximum, or has a relative minimum. In a similar fashion, the second derivative identifies intervals where a function is concave up, concave down, or has a point of inflection, which means a point that's concave up on one side and concave down on another side. So something like that. So it's concave down over here and concave up on this side. So it's switching between the two. Since the second derivative is the first derivative of f prime of x, then the same relationship that exists between f and f prime must exist between f prime and f double prime. So what we have on the next page is the same basic looking function, or the same basic looking table that we had 2 pages ago. So we can fill in this side pretty easily. So if f double prime is 0 or undefined, then f prime of x may be a relative maximum or minimum. If it's greater than 0, then the first derivative is increasing. If it's less than 0, then the first derivative is decreasing. And if it changes from positive to negative, then it's a local maximum. And if it changes from negative to positive, it's a local minimum. And let's just talk quickly about the impact that this behavior on the second derivative will have on the original function. So if it's 0 or undefined, then f of x may be a point of inflection. It also may not. If the second derivative is greater than 0, then the function is concave up. All right, so it looks like that. If the second derivative is less than 0, then the function is concave down, which means it looks kind of something like that maybe. And if the second derivative changes from positive to negative or from negative to positive, then the function does have a point of inflection for sure. The only time we're not sure if it does is if the second derivative goes from negative to 0 and then back to negative, then it wouldn't be a point of inflection. Let's take a look at the same example function that we did in the last video. So we looked at x plus 2 to the 2/3 power plus 1. We found that the first derivative was 2/3 times the cube root of x plus 2. Now let's take a look at the second derivative of that function. So f prime of x was, we wrote this as 2/3 times x plus 2 to the negative 1/3 power. So to find the second derivative, we're just going to use the power rule again. So once again, we multiply negative 1/3 by the coefficient here, and that becomes negative 2/9. And then we've got x plus 2, and we subtract 1 from 1/3. So that becomes negative 1 1/3, which we don't like mixed fractions anymore. We liked that back in middle school, but now we want to write that as negative 4/3 power. And just to make that look a little bit cleaner and make it a little bit obvious how we want to figure out where this is positive or negative, I want to write this like this. So this is going to be the cube root of x plus 2 to the 4th power. All right, so that's using all of our exponent rules, taking exponents back to radical form. All right, so let's think about where this function is defined and not defined again. So f double prime of x, once again, is not defined when x is equal to -2. Because then we've got 0 to the 4th power, a cube root of that. It's all still 0, and dividing 1 by 0 gets us into a mess. What happens when x is not equal to 2? Well, when x is not equal to 2, this thing is not 0, and then we raise it to the 4th power, and since it's even, this is always going to be a positive number. And so the cube root of this positive number is always going to be a positive number. So what's the overall second derivative going to look like? Well, it's going to be this negative fraction times this positive fraction. So f double prime of x is less than 0 everywhere x is not equal to -2. All right. So if we wanted to do the fancy way of doing sign analysis is we kind of draw a number line and we think about -2. And over here, it's negative. And over here, it's also negative. Okay, so negative second derivatives mean concave down functions. And at x equals -2, it's not going to be a point of inflection because it's not changing sign from positive to negative. It's just being undefined. All right, so once again, let's take a look at the function in GeoGebra. And we'll see once again, son of a gun. We'll see once again that this function, just like we predicted, is concave down on this side. It's concave down on this side. And over here at the cusp, the concavity isn't really defined at all there because it's not switching from being concave up to concave down. Okay, so that's the idea of the second derivative and how it can be applied when functions aren't defined at a point. On the next page, we're going to have a little bit of a quiz. Take a look at page 327 and do your best to fill that out in pencil. And we will give you a grade on that quiz that means nothing in the next video.